Bueno, arratsaldeon guztioi eta ongi etorriak izan. Gaurko hitzaldi honekin edo emanaldi honekin irekiko dugu matemozioa izeneko zikloa. Ziklo honi izen hau eman diogu. Matemozio zikloa da ikalau korporazioak, bekam eta bekam berkak, eta Euskal Herriko Unibertsitateko Kultura Zientifikoko katedrak elkarrekin antolatu dugun hitzaldi ziklo bat. Urtean hitzeko zikloa izango denez, aurtengo urteari dagokion hitzaldia gaurko hau izango da. Bienvenidos y muy buenas tardes bienvenidos a esta conferencia con la que comenzamos el ciclo Matemozioa. Este ciclo pretendemos que sea un ciclo plurianual, de manera que con esta de hoy empezaríamos el ciclo de cara también a los próximos años. Y lo hacemos, esta es una iniciativa conjunta de Beckham, el BERC Beckham, la Corporación Tecnológica ICA 4 y la Cátedra de Cultura Científica de la que soy coordinador. Y en calidad de lo cual les doy la bienvenida, puesto que la sala en la que nos encontramos es una sala de la Universidad del País Vasco. Desde el punto de vista de la cátedra, esta es una más de las actividades que desarrolla de promoción de la cultura científica. Actividad en la que procuramos abarcar todos los campos del conocimiento científico, en este caso matemático. No sé si es equivalente, pero para nosotros es como si lo fuera. Y bueno, es una más de esas actividades. Yo, sin más, le voy a dar la palabra a Enrique Zuazúa, que será quien haga la presentación también del conferenciante de hoy. Eskerrik asko, muchas gracias.
Bueno, arratsaldeon guztioi, buenas tardes, good evening. I think there is automatic translation service, but I don't remember from which language to which language. Because there are at least 3 languages we can use, excluding French, Italian and so on, but and then the translator, I don't know what instructions he has. Okay, so in any case for us, is as Beckham, it's a pleasure to have you in here. Thank you for coming. We know there are many activities these days, and maybe there are other things in your agenda. Some people told me they cannot stay until the very end because there is an opera activity afterwards, or more or less in the same time. Okay, so some time ago we were discussing about what as Beckham could do for the diffusion, the public awareness of mathematics and science. This is one of the priorities of the Basque science and higher education agenda that the Basque government has been developing in collaboration with Iker Basque and then with all the other centers that emanated from Iker Basque as Beckham. In the past, we had the privilege of having at least 2 key lecturers in the Foroa organized by Iker Basque. Pierre Williams was here in 2008, and then John Borg, who is today here with us, also from Oxford, was lecturing, I think it was in 2009. At the time he was telling us about the Poincaré conjecture and the very unique trajectory and success of Perelman in this this mathematical Himalaya that the Poincaré conjecture was. Then discussing this issue with Guillermo Dorronsoro from ICA 4, ICA Lau, that I thought he was telling us a few words, but maybe later, no, he says not, he's not saying anything. He's the Vice President Executive of the Alliance of Technological Centers ICA 4, ICA 4, and also with Juan Ignacio Pérez, who is the chairman of this chair for the public divulgation of scientific culture. We thought that maybe it would be a good idea to try to make once yearly, more or less, public lecture, trying to bring to people what the excellence of mathematics that very often is not really well known by many of our citizens, or even sometimes colleagues in other scientific disciplines. So we were struggling about who should be first, and then we thought, oh, why not Alfio Quarteroni? Alfio has been very kind to accept our invitation. Alfio, I will not tell you much because I think it's much better than he talks, and then you will see who Alfio is and what he does. Alfio is Italian. He did his PhD in Pavia, right? In a very distinguished school of applied mathematics. So many applied mathematicians know the 3 volumes of Lyon's Magenes, which are, by the way, very hard to read, but they contain most of the functional analysis you need, and you still need to solve many of the models of mechanics and engineering. And then he soon, at the time he was doing quite, say, theoretical numerical analysis, so this was the more theoretical, say, stream of the panorama of applied mathematics. And then slightly he has developed a very, very unique and successful career in which he has been capable of keeping the highest standard in the content of mathematical content of the research he does, but simultaneously to face extremely important challenges coming from industry and other disciplines. So very recently he has been very much involved in the modeling and the simulation of the human cardiovascular system, something that I'm sure many of us are here concerned, because as soon as you go to Osaki Decha and you do the testing, then you start getting some asterisk about the indicators. So now he's professor at the Università, the Istituto Politecnico di Milano, where he's the chairman of the MOX, of the Laboratory for Scientific Computing and Modeling, and he also has a joint appointment in Lausanne, where he's running another group. I mean, he has many awards. He's director of journals, of book series. He has delivered many important lectures. I remember one of them in particular, the lecture you gave in the International Congress of Mathematicians in 2006, that by the way was opened by Professor John Ball, that was at the time he was the president of the IMU. I think in the inauguration the chairman of the ceremony was the king that was here today, but I think he had to leave. I mean, he could not attend this lecture. And so Alfio, thank you for coming. I hope you will like it, and I hope this will be only one first lecture of a long series. Thank you.
So thank you very much, Enrique, for this great presentation. It's an honor, a pleasure to be here. It's going to be a non-technical presentation. Try to convey some ideas, hopefully simple ideas, on the way mathematics can be used and is used nowadays. Try to avoid any technicality, in particular try to avoid equations, and once I will use equations, this should be just to create emotions. You're not supposed to understand equations. I mean, most of you are not supposed to understand the equations, just to see that equations are behind what I'm saying, basically. The talk is on Galileo and the legacy of Galileo, and is on recent applications of mathematics to our, I would say, daily life. And I choose 3 different fields among the many fields in which you can talk about mathematics today. And these are medicine, technology, and environment. And of course, what people who are not acquainted with using mathematical concepts ask is why math matters, why math is important in those type of fields. And in fact, let me start giving a couple of examples which are, I guess, known to everyone, just to explain why math is, in fact, and the way actually math is behind the scene of what we do very often during our life. These are two examples among the very many, and one is concerned with the internet search and the searching on the web. And of course you have to get an idea about the numbers, the figures here. These are estimated figures. It's not important here to be very precise. It's important to give the order of magnitude of the scale of the phenomena, say. There are about 230 million of websites, and this is an everyday increasing number. And there are about 1,000 of billions, 1,000 of millions of web pages in the net. And there is about 1.5 billion of users. I mean, people who quite frequently use the web just for fun, or for investigation, or for recovering information and data. Now, how can you find what you're looking for? Well, this is just, say, going into a library, a big library, a gigantic library, and asking a lady, a magician, to find what you're looking for, to find the right shelf and get the right information for you. How can you do that? Well, you have what are called the search engines, which are powerful tools that allow to find the information you're looking for. For instance, there's just a simulation. Assume that you Google Isaac Newton, right, or any other information. Well, you see, you find among 1,000 billion of web pages, you found, in this case, 10 million of pages in just 14 centiseconds. And this is what you can experience every day when you Google something, right? And how is that possible? Well, of course, it's a bit difficult to explain to people who are not acquainted with using mathematical concepts of algorithms, but roughly speaking, you can think of having all these pages with different size, and the size is related with their importance, say, and you need to rank these pages, and you need to establish relation between one page and the other, according to the fact that from one page you have a reference to another page, or vice versa. So by doing that, you end up with formulae. Let me say simple formulae, because these are linear formulae somehow. You have equations like those that you find in high school, in which you relate the page rank of a page to the page rank of the other pages that are connected with that. So these are, for mathematicians, simple equations, but the difficulty stands in the fact that you have very many equations. You have virtually many billions of equations. So you have a system of equations in which the variables are all interconnected one another. So this is a system of linear equations of gigantic nature. And once you have to select the pages that are more relevant for your request, you have to extract information out of this gigantic system, more precisely out of this matrix of information. And this is possible because you have very fast mathematical algorithms that are there to extract the relevant information in, we can say, almost real time. And this is why Google has been, for instance, so successful, because it has perhaps still the most effective algorithm to find the page rank of the pages that are available there. And you can say that, by exaggerating a little bit, that the keys of the success of Google is mathematics, is the fact that you have a more powerful mathematics behind it. Here is another example. You have a cellular phone, you want to send a picture. And this seems very natural today, right? You click, you send a picture from your cellular phone, from your mobile phone, and then on the other side you receive a signal, see, warning, you have the picture, and it's a beautiful picture, just like the one that you have been taking on the other side. And this looks to us a kind of gratuity, right? It's so normal, it's so simple, it's so costless. And in fact, what you do is that you start from the picture, from the original picture, you send it to your cellular phone, and you somehow compress it, you digitalize it with a very smart algorithm, and then you send it to the other phone and you decompress it. You pass from these digits to the real picture. So this is handled by two different, again, algorithms that we can call a transform and an inverse transform. And this, more precisely, is what mathematicians call a wavelet transform, is the treatment of signal. It's the fact that you can, in very quick time and in very accurate manner, compress your information, transfer it very quickly, and then decompress it and have it available as if it were taken from that receiving mobile phone. Again, this is something that 20 years ago would have been inconceivable, but even 10 years ago, I mean, this type of precision, this type of accuracy was not available a few years ago. So this explains somehow one aspect of the story, that mathematics is a living body, is a living discipline. I mean, we're not using all the day this mathematics that was produced by our ancestors, right, 2,000 years ago, these big names of mathematics, like Euclid, of Pythagoras, and so on and so forth. This is something that is a living science, like biology, like chemistry, like physics, like any other science that you know, and every day you produce new ideas and new concepts, new models, new paradigms, new algorithms that are then transferred very quickly in our daily life. The problem is that mathematics is hidden behind that. And in fact, there is more mathematics that we can think of in what we do every day. And here is a bit of exaggeration, but not that much. Water is a very essential element, can be described through mathematics, right? These are equations. You're not supposed to understand, I mean, the symbols, but just trust me, that these are equations that are relevant for this type of phenomena. I mean, if you can solve these equations, you can have a very precise information about the flow motion in this specific case. You see, the sea waves, when you approach the shore, can be described by other equations. These are even simpler than those that we have seen before. These are one-dimensional equations, say. You are not there to capture the whole physics, the whole nature, but maybe you can capture the most essential elements, those that allow you to understand the phenomena, and sometimes those that allow you to govern the phenomena. Predator-prey competition, again, can be described or modeled in terms of equations, of reaction-diffusion equations. If you can solve this equation, you have important information on the evolution of species, for instance. And the stripes of zebras, or the appearance of butterfly fishes, again, these, the development of these beautiful structures, which are very repetitive, these can again be explained at some extent using mathematical concepts. So here were a few examples on the fact that mathematicians love discovering the hidden mathematical description of natural events, say. Now, the key is mathematical modeling. What does that mean, mathematical modeling? Well, mathematical model describe the world through equations. So here you have three keywords: math models, word, and equations. Now, word does not deserve any explanation. Math models is the concept that you are creating. And to express this concept in a rigorous manner, you need equations, mathematical equations, like those that you have seen before. So equations are behind the model. And if you know how to solve equation, you can, through your model, describe the reality. Now, what is a model? Well, here is just a joke, kind of cartoon, right? You take the real world, you plug it into a magic box and you extract mathematical equations. So that's the idea of the model, right? You take the reality and assume that you have a magic mathematical box that you can shake in a proper way, and out of this box you get equations. And the equations are there to express the origin of the problem. I mean, equations should be reliable. They should be loyal with respect to the real physical problem. Now, Galileo had a great intuition. Galileo was a kind of very versatile scientist in his era. And he made very incredible discoveries, and he had very deep intuitions. And he is one of those, right, which is taken from his Saggiatore, the Libro della Natura, the Book of Nature. This was 1623, and he crafted one of his famous metaphors. And at that time, he used this metaphor to defend the work of scientists from religious authorities. At that time, they were very overwhelming and very, very present in Italian life, say. And you know that nature is a book written in the language of mathematics. If we cannot understand that language, we'll be doomed to wander about as if in a dark labyrinth. So we need to understand that language, otherwise we'll not know which kind of way to follow, right? And in practical terms, this captures our sense that nature truths are somehow imposed on us. They are there already. We have to discover. It underlines the key role played by mathematics in catching and expressing those truths. This was the intuition, say. Now, this is just a kind of synthetic reproduction of how his thought, of his intuition. Actually, Galileo thought about what he called sensato esperienze. So this means observation of phenomena and providing data to measure this phenomena, to use mathematical measures of the phenomena. And then through the induction step, he formulated theoretical hypotheses. So that's the way the scientific method worked according to Galileo. You start from experiences, you use quantitative information, and you extract an hypothesis, an assumption, a conjecture, say. Then you use the deductive step, the deduction, and you need to provide what he called the necessarie dimostrazioni, necessary proofs, right? And this is the rational step of science. You have to base your reasoning on logical mathematical arguments. And now you need experiment, what was called at the time the cimento. You have to either verify or express your refutation of your conjecture. And if you accept it, if it is verified, then you have a new law. You see, a new hypothesis. So this was in a nutshell, the basic step of the Galileo intuition. Now, can we establish a parallelism between this structure, conceptual structure, and what applied mathematicians do today when they use mathematical models? So Galileo was somehow expressing the concept that you have a reality from one side, and then you have this representation from the other side. Today we'll call this representation a model, right? You have the science from one side, and you have the metaphysics from the other side. So how can we express this in modern language? Otherwise said, what does an applied mathematician do today? This is very much inspired by the Galileo idea indeed. You start from data. Well, this is the case of an application in a medical context, but it doesn't matter. You may have here a car or a flood. You have data, and data can be certain or uncertain. They might be affected by uncertainty. You have to create a mathematical model to create equations using that magic box to produce equations. Now, these equations stem from basic understanding of physics or biology, chemistry, right? I mean, you have to start from basic principles, and you express them by conservation of forces, or conservation of momentum, or conservation of mass, just to make an example, and then you express this conservation principle through equations. And most often these equations are partial differential equations because they express variation in time and space of relevant quantities. Right? I want to see the way electromagnetic waves that are generated by our cellular phones or by lights in this room are propagating. And they propagate in space and time. And they propagate according to given principles. And to express variations that are infinitesimal in space and time, you need partial differential equation. That's why it's so difficult, because these equations very often are so difficult that you cannot even solve them by paper and pencil, like we were used when we were at high school, right? So you need to accept a mediation, a compromise. You need to represent this virtual world with a numerical world. You have to express these equations in a simpler form that could be accepted by a computer. You need to go to the computer. You need to solve your problem on a computer, right? And there is a lot of room here for mathematics and for different fields of mathematics indeed. Once you have a solution, you have to decide whether or not you are happy with the solution. And here is the way. You have this cimento of Galileo, you have the feedback. And the feedback is through validation and verification. These are two magic words today. What is verification? Well, verification is the step according to which you decide whether your numerical model, your reduced model, is coherent. Mathematicians say convergent to the mathematical model, the one that you would have loved to solve but you cannot solve, right? So this is verification. This step is endogenous to mathematics. I mean, it's within mathematics, right? And this is the realm of mathematicians to go under this verification step. The other step is more challenging, is validation. You have to compare what you have been obtaining with these models, mathematical models, with the real story. And the real story is the real measures that you may have on a given phenomenon. For instance, the electromagnetic waves here, or the presence of a drug in the blood for the previous example. So here is where you have to check to decide whether your model is good enough. And once your model is good enough on a variety of representative problems, then you can be comfortable in using this model for every problem of that class. And this is the synthetic, step of the Galileo procedure. So you have to create a model that passes the test on some simple but clear, rigorous examples. And if you can do that, then you can rely on your model and use it for a variety, for a plurality of problems, even those that you cannot even think of at the time you are developing your own model. So this is the idea. So what is next here? All right. So math is an immaterial laboratory. Right? Once you know how to set up your equations, then you can play in your lab, which is the lab of mathematicians. You don't touch the real matter, right? You just play with equations. And that's why at the very end you have to make sure that you can validate your model against the reality. But as soon as you are in your own office, in your own department, you are on your own, then you can play with mathematics. You can play in a consistent manner with the mathematical tools that you have been creating. Math is non-destructive. If you want to see the way such an important monument could resist to, say, a seismic wave, you have first of all to create the model, the geometrical model of this piece of element, and then you can, for instance, create an artificial, you see, impulse there, just hammering by a mathematical hammer, and see the way this wave is propagating through the Colosseum, for instance. And of course, if you want to see the way it resists to stronger hammers or stronger solicitation, then you just have to change the force. But this, again, is not destructive. You do not have to go under the real simulation. You can use mathematics to try to predict the effect of seismic waves when they propagate. And here are a couple of examples among the many, very many. These are a couple of examples in which you have data. So we can compare them with real data. This is a bridge, one of the old bridges that are in our Mediterranean countries, say this is in Liguria near Genova in Italy, northern Italy, and here is a mathematical model of the bridge. Actually, this is a geometrical model of the bridge that you see here. For those who know the matter, these are spectral elements, which mean elements in which you look for a solution, and you represent the solution by high-degree polynomials, because you want to make sure that your waves are propagating with the right speed and with the right, having the right amplitude. This is preliminary to the computation. Then you have your equations that I'm not showing here, and this is a result of the seismic wave. I want to see the way you see the seismic waves that are propagating in the terrain affect this the formation of the bridge. And please note that there is an amplification of a factor of 5 just to make more visible. But this is an important deformation of the bridge, right? So here we are coupling the seismic wave propagation with the solid mechanics for the bridge. Of course, you can simulate different types of scenarios and see the way this bridge will resist, and see which are the critical points and where you may have to reinforce the structure of the bridge to resist more important solicitations. That's another event. This is in New Zealand. This is Christchurch. It's one of the most important cities in New Zealand, and this is a earthquake that occurred in a year ago, right a year ago, and the energy was 6.2 on the Richter scale. And now what we have been doing here has been to simulate the effect on the city itself, on the main district, the central business district of the city. So we are solving the problem in a big portion of the terrain here, 60 kilometers by 60 kilometers by 20 kilometers. This is the layer, the upper layer. And then this is the place where you have the city, and in the city you have in particular, this is a 600,000 inhabitant city, and in particular the most central place is this central business district. And here again, we wanted to see the way this district reacted to the, because we have data, right? We have data and we want to reproduce a posteriori, of course, the phenomena. Now what you see here is the propagation of the seismic wave near the central business district. You see the houses, the buildings there, and you see different colors. The colors refer to the intensity of the velocity. The velocity here in the buildings goes from 0 up to 100 meters per second. Is much lower than the velocity of the propagation of the wave, which is order of several tens of kilometers per second, but still it is important. And what the interest of this investigation was to see the way this building individually reacted or could react to other seismic phenomena. And you see the color, again, red is the upper part, the highest part of the scale. And you see the way they are moving, and there is an amplification factor of 20 here. So what you see is not the reality, it's the reality multiplied by 20. But still you see the different way they color, right? And when you go to the upper part, you have more red because you have more oscillation, you have more velocity. And what is important to notice here, I'm not going to show it because it's too technical, is the way the city returns the energy to the ground. Unfortunately, it returns most of the energy. So it only captures a very minor portion of the energy, of the total seismic energy, because otherwise, if it would absorb too much energy, then you will have major distraction. Again, you can use these tools to make prediction. And you can easily guess what type of importance those type of investigation might have on, I would say, also the regulatory level. We use math for human life, and we use in particular math for better understanding the cardiovascular system. And the idea is not only understanding the way blood flows in our arteries, but trying to then address some specific clinical problems in which you have some pathological events, and we like to see the way these pathological events are created, they develop, and the outcome possibly. You can also use it for virtual surgery to train a surgeon to use to describe scenarios without, of course, being invasive with the patient. And we want to use it for, and we do use it for the design of prosthetic implants, like for the design of aircrafts or of airplanes or of cars, right? And you have to put a bypass, for instance, a coronary bypass. We like to shape the coronary bypass in a way to reduce the turbulence that is created downstream. So there are many possible applications. Here is just a picture that is very old. I always show it because it is very simple, but it already addresses part of the complexity. This is the carotid bifurcation. The carotid, we have all of us, we have two carotid arteries in our neck, and they bring blood, in particular, to our brain. And here is a bifurcation, and behind the bifurcation, you have flow recirculation. This is not only for blood flow, it's also in river. And when you have blood recirculation and flow recirculation, if the density is high, for instance, because it's too fatty or too much cholesterol, then you may have the formation of a stenosis, of an occlusion, and that's very important. So this is an healthy patient. This is a single heartbeat. And this is the systolic peak, and this is the diastolic peak. And you see the way the velocity profile behaves in an artery which is healthy, but rigid. So this model is for a rigid artery. Reality is that arteries are not rigid, they deform, like this one. This is the same carotid as before. It's just a different view. However, in this case, you have a deformation of the artery. And here the problem, mathematically speaking, is more complex because you have a flow, a blood flow, and we have, so you have fluid dynamics, and then you have the mechanics of the soft matter of the walls, arterial walls. And you have the interaction between these two elements. Right? So this again is the simulation of an healthy patient. You have a few heartbeats, you have a pressure wave that is propagating, you have the deformation of the artery, and the colors refer to the intensity of the velocity field. So red means high velocity, blue means low velocity. Okay? Now, this is just a piece of the story, but of course you're interested in having more general views. This is the ascending aorta. Heart is somewhere here. These are two heartbeats. You go from 0 to 1.7 seconds. So these are the streamlines. You see the complexity of our blood. And this again is for a healthy artery, which is deforming. So these are the strict lines. You see the particle trajectories. And this is the deformation. You see the displacement. You go up to 4 millimeters, which is a big displacement actually, of the external wall. That's the way our artery deforms under the action of the heartbeat. These are tremendously complex computation. It takes several weeks on a big supercomputer to simulate, you see, two heartbeats. And you understand how far you are from reality if you really want to solve the problem for a long time and on the whole body. How far we are. On the other hand, you have to invest, you have to see, you have to start understanding basic issues, and then you have to develop ideas on how to move from the local analysis to the global analysis. This is very crucial. Here is another example. Now this is the idea of bifurcation, and often, again, since you have an occlusion, which is represented here by this fatty material, you can create an artificial bypass or graft. And in this case, what counts, what's important is to try to optimize or at least to improve the shape of the bypass to have a better flow downstream. So again, this is the healthy case, but then I'm not going to show it now, but we have the case in which you put the bypass and you see the way the flow behaves. Now, as I was saying before, this is a local analysis, but in fact in our body there are thousands of large arteries and several billions of capillaries, so small arteries. So how can we use Navier-Stokes equations, mathematical equations, for solving all this complexity? And this is the way we've been proceeding. We started from local three-dimensional analysis, for instance, the carotid bifurcation, because then we want to understand the whole feature, and then we use one-dimensional models for the most important arteries and veins, the red and blue. And when you go to the level of capillaries, not even one-dimensional models are suitable. We have to use this green spaghetti, and actually these are the capillaries that we represent through ordinary differential equations, and we use the analogy with electrical circuits. So this is a new type of mathematics that you have to somehow create, invent, use in order to face the complexity. Otherwise you'll never be able to solve the complete picture. And here is the way it goes. This is a pure one-dimensional model of 100 arteries in our body. What they are describing here, and here is a zoom, the pressure wave propagation in this system of one-dimensional arteries. So we're assuming that every piece of our artery is assimilated to a one-dimensional channel, and we solve a system of one-dimensional pieces. This is much faster than solving the three-dimensional problem. In a few minutes, you solve the blood propagation in the whole body with less accuracy, of course. But you have to accept the compromise if you then want to do something more sophisticated, namely to combine 1D and 3D. You see, this is a piece of our artery. Of course, it's a simple artery, this one, not as complicated as those that you have seen before. The previous arteries were taken from real patients, so these were from real data, real data. So this is a three-dimensional artery that you can break artificially and create a one-dimensional continuation. And now you have 3D and 1D. But you have to create this coherently from the mathematical viewpoint, which is not easy. But if you can do that, then you can afford much higher complexity, like in this case. You see, this is an important part of our aorta, and these are branches of our aorta. This is the mesenteric, this is the right renal, this is the abdominal, and this is the thoracic, and so on and so forth. Right? So this is the red part is the 3D. The other colors are 1D. And we are combining together the 3D and the 1D because of the fact that 1D is so cheap to solve. And here is what we do realistically. We start from 1D everywhere, and we overlay this 3D from a real patient. So somehow on the background you have a virtual patient, an average patient, say 175 centimeter tall and 60, 70 kilos weight and with specific characteristics. And then we overlay this data which are taken from a real patient. And these are three-dimensional data, and then we solve the problem altogether. So you see the 1D coupled to the 3D here, and here you see the tail of the 3D. So this is very important because otherwise you need this boundary condition that you don't have. When you solve differential equation, you need boundary conditions, but here you cannot chop your patient to compute boundary conditions, right? So it's the one-dimensional system that provides the boundary condition. And there is a feedback mechanism. It's an integrated mechanism. Here is the way you can use these models to predict the evolution of this, you see, aneurysm. This is an aneurysmatic sac. This is a pathological dilation of the artery in the brain, and you want to see whether this could resist over the years and could get stable or could break. And of course, that's a major issue for a clinician, for a neurosurgeon. And here is the same type of aneurysm, but now you have an analysis of the Walsh stresses that are the forces acting on the aneurysm, and you want to see the way you can reach critical values of the Walsh stress and to understand whether or not this should be operated. Now, operating a patient is difficult because now you have to go into the brain and of course you take risk. And with mathematics you can not solve the problem, of course, but help the doctor to better understand what is going on. Or like in this case, this is the so-called ventricular assisted device for a kid which has a dysfunction in its ventricular activity. You have to provide blood because otherwise blood will never be exposed from the heart, ejected from the heart with the right flow rate. So you create this, you have this extracorporeal pump, and then you inject blood through this VAD, ventricular assisted device, which is an artificial, you see, appendix like this one. And here the issue is how should it be shaped? What is the optimal form of this appendix? And how can you fit it by this external pump? So it's not only the shape, optimization of the shape, but also somehow the optimization of the boundary condition, the inflow condition, say. And of course, what is important here is the fact that you have to inject blood, which then goes to the upper limbs, but also to downstream here, because coronary is the part from there, so you have to feed the upper part of the body, but also the heart itself. And it's a difficult, again, mathematical problem, because you start from the real patient, so this is from the real patient, this is the cannula, the external cannula, which is artificial. This is mathematical model, this is the finite element description, say, and here is a detail on the streamlines. You see how complicated its flow pattern to predict. And here is the way you inject blood, and it goes to the upper part, it also goes to the lower part. You have to make sure that this is enough to irrorate heart through the coronaries, for instance. So you have very many aspects that are tied together. Of course, when you go to the brain, it's even more difficult, and here we're very far from having a clear understanding what is going on, but it's just preliminary investigation on the way you can describe what's happening in the circle of Willis, which is again described through a one-dimensional set of arteries. And in particular here we are simulating the case in which one of these vessels are occluded, and the way the brain distributes blood it uses surrogate vessels to distribute blood. So you see here the heartbeat and the way this is affected through the pressure field, and here is these are the isosurface of the oxygen. Of course, there's a very simple description of the brain. We're just assuming a kind of porous media law for the brain, but then you have to integrate the fluid equations into the circle of Willis with the perfusion into the external tissue. We have been using mathematical models for sports in many different environments. Here is a few of them: Formula 1 cars, rowing boats for Olympic Games, swimsuit, and America's Cup. Now, in this case, of course, the objective is completely different. You see, the goal is totally different. But again, you are playing with equations, with mathematical models, and you want to create an environment that is capable to predict, in this case, optimal behavior, improving performance. Now, for the swimsuit, the matter is how to create a swimsuit that is capable of reducing the viscous stresses due to the turbulence that is created by the swimmer. It's a very difficult task. You see, you explore all possible situations. In particular, you want to eliminate completely the swing, and this was the case for the last Olympic Games. You just use a bonding technique. You want to eliminate the swing, because even this tiny swing is creating kind of resistance. So how can you find the optimal patchwork of the swimsuit, and how to find the optimal constituents, and how you predict then the performance. In the racing cars, well, what is perhaps not that known is that today the performance is due to, roughly speaking, say, the 50% of the aerodynamics of the shape, and the 35% to the weight, so materials in particular, and 15% of the engine and the propulsion. So aerodynamics still play an incredible role in the improving the performance of a car. And that's why today, to develop a Formula 1 car, you spend most of the time, say, in your lab, by making simulations, and you just use 1 month, most 1 month and a half or 7 for the practical construction of cars. Right? Now, perhaps what we can say at the end of this discussion is that math is our lab. Right, and it's cheap. It's cheap because you don't have to make big investments, and this is also true for the research, right? I mean, you have to invest on the brain of the people, but you don't need very many. You don't need important and expensive infrastructure. It's fast because you can predict the output, predict results in a very fast way, and it's optimal. It's optimal because you can play with all these deep mathematical concepts of optimality, right? You can describe different scenarios. You can play with parameters. We can play with data and reproduce different types of scenarios, and ending up with what is considered to be an optimal solution. Well, I don't know if you can a few more minutes, or if I should stop here? Okay. This is another extreme application, and I'm very proud that at least at the very early stage, we have been behind it. The development of the solar impulse. This is an airplane that was developed and conceived at EPFL, and is completely empowered by solar energy. And this was a major effort in terms of science, in terms of technology, because you have to develop not only optimal shapes, you have to develop optimal new materials that are not available. We have been working for the America's Cup, and there have been this possibility to experience the way the sports in competition provide extremely important stimuli to mathematicians, to scientists, because you have to strive with new materials, new technology, new rules for the games, and definitely new type of mathematics, for instance. This was the first America's Cup that I've been involved with in 2003. This was in New Zealand, in Auckland, and this is the second one in Valencia, and this is the third one where we did not win actually at the very end, but it was also extremely important because the concept was completely different, and this was the multi-hull instead of a single hull. So this is the idea you play with. You start from the real stuff, from the drawing of an architect. We have to create a geometrical model to create this triangulation, finite element triangulation, for instance, and then you use your equation, and with this equation you solve the problem, and you try to extract all possible information out of the problem. What kind of information? Well, the goal is to reproduce the complete flow pattern, because if you can reproduce the complete flow pattern, you can, for instance, with this free surface that is created, you can decide, you can see what is the wet part of the hull, and therefore you can see what is the water resistance. You can compute forces acting on the appendages and on the sails. These are the appendages of a classical America's Cup. This is the Alinghi that won in Valencia in 2007. This is the keel, this is the bulb, and these are the winglets, and this is the rudder. So it's a turbulent flow, and that's very different than what you have in our body. I mean, in blood is almost never turbulent, while here it is turbulent, and catching the turbulence or the turbulent behavior or the separation, the transition between laminar and turbulent is extremely critical here. You have to understand the way sails deform under the action of the wind. And here you can see the way mathematics is versatile. The algorithms that we have been using for the arteries to compute the deformation of the arteries under the action of the heartbeat are, roughly speaking, the same as those that we have been using here. Because here again you have a fluid, which is air, it's not blood. You have a solid material, which is cell, it's not artery. But the physical laws that are governing their interactions are the same. So the mathematics which is behind is about the same. Of course, data changes completely. The type of picture that you have at the very end is totally different, but you do not have to reconvert yourself from being an applied mathematician in medicine to an applied mathematician in engineering, in hydraulic engineering, or in sport, right? I mean, most of your heritage, most of your know-how can be readapted quickly. And I think this is an important message for young people. I mean, you invest in understanding, in basic understanding. You have to understand the basic conceptual kernels that are behind phenomena. And once you have a very deep understanding, you can try to transfer this to many different and diverse environments. And I'm not saying that it's easy, okay? It's not easy at all, but it's possible. This is the 2010, this is the catamaran, this is gigantic technological enterprise, and we have to strive to reproduce completely different type of fluid dynamics around the catamaran. And again, it was very important because the behavior of the physical behavior of the flow field is very different. However, the governing equations are at the same time. So most of the previous effort had been used for these new competition as well. So this is an old picture, but it's just there to reproduce the complexity. These are two boats in competition. One is following the other, and the one that follows is the one which is more red because it has more pressure. Pressure is higher. It takes more wind. So here, what you have to solve is the fluid in the whole environment, in the air, in the water, on the free surface of the water surface, and you can do something better. You can also create algorithms to put in the hands of the skippers to decide the way they can behave according to the behavior of their opponent. Right? This is game theory. Right? This is a completely different type of field of mathematics, but it is behind and can be used also in that case. So I think I used all my time, and I'd like to close here by putting Galileo on the Alinghi boat. I think most of many things that we learned from him have been actually used to develop our conceptual approach to the problem and eventually to find the results. And by that, I would like to thank you very much and very warmly for your attention.
Okay, thank you, Alfio, for this delicious talk. It is now time for questions or comments.
Okay. For example, if when you take the cardiovascular system, of course you take a small part of reality. You have 1D arteries. I don't know if the blood is a complex fluid or it's not like water. Blood is not like water, and so on and so on and so on. But the question is, how can you obtain good results from so many approximations?
How reliable are our results, right? It's an absolutely pertinent question. I think we have to be extremely fair and intellectually honest here, and saying that the precision that you can obtain for the boat or for an aircraft is totally different than the one that you can get for a living body. For an aircraft, if you want to find the optimal shape of an airfoil, you know that you just have to struggle with the mathematical difficulty, but once you solve the problem, you can rely on your results, up to the precision that you decide a priori. If you have a living system, it's a completely different story. First of all, because of the so many assumptions that you have to make. Blood is not a Newtonian fluid. It's a non-Newtonian fluid, not even a fluid, right? Because of the red cells and white cells and the platelets. But in large arteries, you can assume the Newtonian behavior and you are not wrong. I mean, you are not macroscopically wrong. You are in the entourage, in the environment, in the voisinage of the reality, right? You don't have precise geometries because geometries are taken from MRI or CT scan, and today machines are not fully accurate. You can estimate that the uncertainties are the order of 2%. Now you move from there, you have an inexact geometry. Well, actually, I'm talking about not on the deformation, but on steady case. Say, assume that you have a steady, say, take the levers, say, right? Then you know that you are aware of the fact that you are playing with a geometry that is not exact. And you know the way, because especially the way fluid dynamics equations depend on the geometry. I mean, the tiny change in geometry can produce important changes in the solution of Navier-Stokes equations, for instance. You have all the material characteristics of a single patient that changes, right? That change. So you have all this complexity, and it will be an illusion to pretend to deliver a result which is accurate. But this is not the goal. The goal here is to help doctors to better understand, on the basis of quantitative arguments, some aspects of the complexity of blood picture in this case, which would be very difficult to achieve otherwise. For instance, the wall shear stress is a quantity extremely difficult to measure in the lab, in the hospital, right? And it's very important from the fluid dynamics point of view to see the way an aneurysm would resist in time, for instance. If you want to optimize a bypass, you optimize mathematically the bypass, and you can rely on this optimization because it's based on very solid mathematical arguments, but the data around this are uncertain. So, to conclude, you have to be aware of the fact that here you are providing indications that can help, but that should not be taken faithfully, like those that you take for the boat or the racing cars and or the seismic waves, for instance, because you know much better the fundamental governing equations. But still is a very important type of information that you can provide.
Could you tell us how much of these computations one can do by, so I go to Corte Inglés. So if I go to Corte Inglés, I buy a computer and then I buy a software, say Fluent, or there are commercial softwares that are actually very expensive, right? And people use them in industry. And so could I do the same thing?
Okay. It really depends on the answer that you want. In the sense that let me start from a dream, okay, and then I try to go back. My dream is that tomorrow may be not on Wednesday, but not even in 20 years from now, because you're busy tomorrow. You're busy tomorrow. You're very busy tomorrow. So the day after tomorrow, say in let's say 10 years. Let me take a safe margin. 10 years. In 10 years, doctors will go to the hospital with their cellular phone, smartphone, and they will go to see a patient, and instead of having this table with all information on the patient, they will have their cellular phone retrieving the information on the patient, retrieving graphs and pictures and simulations and the probability of outcome of certain diseases. Because this cellular phone is the storage is large enough to incorporate pre-computed solutions. All right? You should not pretend to put this Navistock stuff in the server phone. But perhaps you can pre-compute solutions and then using smart mathematical tools like reduced basis methods to work on, in real time, from real patient on a space of much lower dimension, by exploring the pre-computed solution that you have stored in your server phone. So I think that there's a lot of room to merge or to coordinate very expensive computation which are on the forefront of the scientific research with their usage. Okay? And mathematics, applied mathematics, is also there in these days to find a way, by principal component analysis, proper orthogonal decomposition, reduced basis methods, to go from the high complexity to the real-time solution. So my idea is that we have to continue investing in the academic environment by looking at very ambitious answers using full power of mathematics, because you have to understand what is behind the scenery, and then developing methods that make all this accessible to a small computer, even to a cell phone, because I think that the breakthrough is that tomorrow people will be able to use their cell phone not only for sending images, but also to envisage scenarios. And mathematics should be much behind that. So there is a transition, in my understanding, between the most complex simulation and the simulation that you can reproduce in real time on your things. And this transition is covered by new mathematical ideas.
Thank you very much. Have you any experience in modeling natural ecosystems?
Not professionally. I mean, when I teach to students in Lausanne in life sciences, I motivate them by systems for taking from ecology, say. So we play with these systems, and but we play in an amatorial way. I mean, I never worked myself on this problem up to the level of facing very complex cases, and which are on the forefront of the research and producing reliable results. So we can use these methods because behind these are systems of, say, reaction, diffusion, convection, which are the same nature as some of the equations that I've been using. So it's not a different type of mathematical word. It's the same mathematical word, but I never worked in a professional manner, so I never dealt with real data for that.
Any other question?
Maybe just a final brief comment related to the question that
Iñaki was asking. You
have shown simulations on
problems that are
very much on real time, right? So the boat.
Is it working? Yeah. So the boat or the blood flow. What about long-term calculations? So, for instance, nuclear waste, climate change. Stephen Hawking was telling us recently that within 1,000 years we will have to leave the planet, right? So, can this methodology be used in order to compute very long-range phenomena? Or there is enough, not enough sufficient computing capability or accuracy on the methods we developed so that this can be done?
Yeah, I think what of course is relevant is the characteristic, what is long and what is short, right? Is the characteristic length of the phenomena in time and space, but here we're talking about time. If you take the heartbeat, it's every second, right? And in fact, if you want to solve the complexity, the characteristic time is order of 10 to the power minus 3, 10 to the power minus 4 seconds. So what you really have to resolve is a scale of that size. Okay, is that small scale, large scale? Is it a long time? Is it a short time? Well, it's a short time because if you want to simulate, say, 1 minute, it's a short time. But mathematically speaking, it's a long time because of this breakdown in terms of the characteristic scale. If you take the seismic propagation, you want to see the way a seismic event concerns a landscape like the one that I've been showing, 60 kilometers by 60 kilometers. This again is a long time because of the frequency of the phenomena. It's a long time. So you need to, if you want to provide reliable results, you need to rely on two different, I would say, ingredients, mathematical ingredients. The first one is that your underlying mathematical system should be stable enough, capable of capturing stable phenomena. And this is the case for these examples. If you want to decide, if you want to simulate the way the climate will change our life in the future, I'm sorry, I missed the second ingredient, which is important. The first one is that your equation should be capable of handling the potential instability. And the second one is that your numerical method should be stable and accurate enough to make sure that you do not miss information. Okay. Now, if you go now to the change, global change. Now here the problem is different because can we rely on available today mathematical models for long-term atmospheric dynamics? This is a big question, right? And if you look at the way people produce meteorological forecast this day, if you go up to 4 or 5 days, say 1 week as the very limit, well, you use deterministic methods, basically, but you integrate them with statistical analysis. Okay, I mean, the result that you see in the television are not based exclusively on deterministic solution of the atmospheric equation, say. You mediate them with the statistical analysis because you want to take track of the past, of the information, of the knowledge, right, of your knowledge. If you want to go beyond 1 week, they make prediction, I'm not saying for 100 years from now, but for 1 month, statistics plays a role which is becoming more and more important. So at the very end, the deterministic part is almost irrelevant. Now, if you have to go on the, say, on an even further period of time, you cannot use the Navier-Stokes equations, basically. You cannot use the shallow water equation for the atmosphere, or you can use them, but you have to complement them with describing scenarios. So first of all, it's stochastic differential equation, and secondly, again, you have to mixing it up with statistics. Now, statistics, this is the way I perceive it, is computed on the basis of the past, what happened in the past. Right? So you understand that if you have been experiencing a very stable period with the coarse regular fluctuation, statistics is extremely important in the modeling part of the story. But since you are experiencing very abrupt changes, the impact, the role of statistics is more questionable. And I think this is where today people are suffering. I mean, people are developing methods for the future are suffering because it's a matter of finding the right compromise between different type of approaches, and you are on a very shaky ground. So this is upstream, and then downstream you have numerical models that have to be adequate, and you're not even there, right? Not there, not even for the numerical models. So I think there is a lot of room for improvement.
Yeah, so I see there is plenty of work to be done. So this is good for young mathematicians to know, right? So they have plenty of open problems to work on. Okay, so Orfeo, it has been a great pleasure. Thank you for this.
Thank you for your attention.
Thanks.